Good morning. Stream is live. We should be getting our preview window. Yep, there it is. Mobile dashboard is up and running. Perfect. So we've got everything set up. We've got our a chat window over here. Hopefully it is again working today. And we finished chapter 15 last time. And that's super exciting because that was about smart pointers. And while those are like really interesting, we're going to be moving on to concurrency this time, which is going to be, it's going to include a lot of different things. Also, what might be interesting is, are they going to be teaching us about async await? Because that is something coming up in Rust, which is also super exciting, but I don't know too much about it in Rust. So I did put a call out for anybody to leave comments in case they knew how refcell or RC might be used in a real life project. Good morning, Stacking. And Danny Fritz commented. So he commented on yesterday's video. He said, a good example of needing shared immutable state from RC refcell T would be a graph algorithm that needs to modify nodes but can overlap in visiting nodes. As long as you can guarantee you won't try writing to it simultaneously, you can use a refcell to lock it. No, they won't teach features in this chapter since it hasn't passed the RFC yet. Oh, that's too bad. I guess like when they pass the RFC, I'm gonna come back to whatever resources that are they're releasing also to help understand it and then go from there. Anyways, shared mutable state, like the graph algorithm. But again, like I kind of wonder, would I be implementing a graph algorithm on my own under normal circumstances, or are there crates for that? I mean, I would guess normally there are crates for graph, for like the graph data structures and algorithms that would normally be used, and then I would only implement my own if I'm trying to like create a library or a crate that like dives deep down. Good morning, Miguel. So I did ask also another Slack channel that is filled with Rust people in Denver, and they have not responded there. Although there's not too many of them in that channel compared to like the rest of the Slack, so that's not terribly surprising. I think the last message was from like a little short while ago. Please let's talk about data algorithms again. I watched yesterday's stream and yikes. Yep, that about sums it up. But we're on to concurrency, so that should be pretty fun. Let's dive right into it. So, handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts has been difficult and error-prone. Rust hopes to change that. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Therefore, rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless Concurrency allows you to write code that is free of subtle bugs, that is easy to refactor without introducing new bugs. Note, for simplicity's sake, we'll refer to many of the problems as concurrent rather than being more precise by saying concurrent and/or parallel. If this book were about concurrency and/or parallelism, we'd be more specific. For this chapter, please mentally substitute concurrent and/or parallel whenever we use concurrent. So, the difference between concurrent and parallel. I mean, if we look at the definition of concurrent, does this browser have that? No, not really. Let's go take a look at definition concurrent. So happening or done at the same time. So like a traditional thought might be you have two processes and they truly are being done at the same time. As in there's CPU processes working on them, so it doesn't take any extra time for it. Let's take a look at parallel processing definition. A mode of computer operation in which a process is split into parts that execute simultaneously on different processors attached to the same computer. So, then we could come back here. Let me make sure that we have concurrent processing. Concurrent processing is a computing model in which multiple processors execute instructions simultaneously for better performance. Concurrent means something that happens at the same time as something else. Concurrent processing is sometimes to be synonymous with parallel processing. So when they're saying like, hey, think about like both of them, well, like the definitions are also saying think about both of them. So it is like difficult for me to come up with a parallel processing that's not concurrent. If I remember correctly off the top of my head, concurrency means we have shared state, where parallel means they can run without shared state. Oh, interesting. Okay, so that's part of a definition I'm not aware of, but that also might be something like some other parts of programming with concurrency that I've not done before. But that's super interesting to keep in mind. I wonder if what if there's like other resources for Rust with this that would split the difference up subtly. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher-level languages, because a higher-level language promises benefits from giving up some control to gain abstractions. However, lower-level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Here are the topics we'll cover in this chapter. How to create threads to run multiple pieces of code at the same time. Message passing concurrency, or channels and messages between threads. Shared state concurrency, where multiple threads have access to some piece of data. The sync and send traits, which extend Rust concurrency guarantees to user-defined types, as well as types provided by the standard library. Let's get into it. Using threads to run code simultaneously. In most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously. The features that run these independent parts are called threads. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time. But it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems, such as race conditions, where threads are accessing data or resources in an inconsistent order. Deadlocks, where two threads are waiting for each other to finish using a resource the other thread has, preventing both threads from continuing. Bugs that happen only in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Programming languages implement threads in a few different ways. Many operating systems provide an API for creating new threads. This model, where a language calls the operating system APIs to create threads, is sometimes called one-to-one, meaning operating system thread per one language thread. Many programming languages provide their own special implementation of threads. Programming language provided threads are known as green threads, and languages that use these green threads will execute them in the context of a different number of operating system threads. For this reason, the green threaded model is called M to N model. There are M green threads per N operating system threads, where M and N are not necessarily the same number. Each model has its own advantages and trade-offs. In the trade-off most important to Rust is runtime support. Runtime is a confusing term and can have different meanings in different contexts. In this context, by runtime we mean code that is included in the language in every binary. This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they often mean small runtime. Smaller runtimes have fewer features, but have the advantage of resulting in smaller binaries, which make it easier to combine the language with other languages in more contexts. Although many languages are okay with increasing the runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. So that's pretty dense of what they're talking about here, but basically, in the last couple paragraphs, they're talking about that different programming, like there's these two different theories that programming languages have adopted of how to do threading. One is the language just calls pthreads, the operating system method of doing it in Linux at least, and the operating system spins up the thread and handles everything there, and the language doesn't have to worry about it. Makes the language a little bit simpler, but the language can't like customize how threads are used either. And then there's these green threads where you can say, "Hey, language, I want a new thread," and the language can say, "Great, here is your thread," but it could be having an entire thread management system built up that may not actually call a thread. Like it may do some other thing to it to make it seem like it's in a thread. That's why we can have the M to N, where we have M number of like one side. So like maybe we think that we have 5 threads, but we really have 4 or 3. Or maybe we have even more threads available to us, but we're not using them right this second as holding them. There might be some like interesting things going on behind the scenes. The green threading M-to-N model requires a larger language runtime to manage threads. As such, the Rust standard library only provides an implementation of one-to-one threading. Because Rust is such a low-level language, there are crates that implement M-to-N threading if you would rather trade overhead for aspects such as more control over which threads run and lower costs of context switching, for example. Now we've defined threads in Rust, let's explore how to use the thread-related API provided by the standard library. So another interesting thing with threads, I had previously said that like a thread on a there's a difference between a thread and running on a different core, but they might be very similar to each other. Pthreads, basically what happens when you call the operating system will make a decision and like tell you, like sort of pretend that it's a thread, but it will actually run over different cores. And that is like true concurrency, because a different core has essentially the ability to run at the same time. Threading traditionally wasn't able to run at the same time, because it's like it's one process, it's one core, but like multiple threads within that core. It's essentially a single CPU running across them. And so previously it would like, okay, I'm going to run a little bit across each one, which might not truly be as fast unless some threads were paused because they were waiting. In that case, then it would be faster because you don't want to have everything bottlenecked. However, Intel has done a huge amount of work recently, and I was wrong last time when I said that threads don't really have that like true concurrency model. In some operations they do. And Stacking, you're saying, I wonder if the Intel meltdown problem will mean green threads will have to go bye-bye. And that's a whole nother topic for this time. I mean, we don't know. Like, we don't know what's going to happen. Intel recently paid out $100,000, over $100,000 in a security, basically, oh, what is that? Where they have a security payout for their bug finding system, security bug finding system. We don't know what bug that is. It might have been for, yeah, bug bounty. That's it. It might have been for Spectre and Meltdown, but it could have been for something else. So we're eagerly waiting. Eagerly? I don't know if eagerly. We're waiting to see what fixes are going to be put into place, and then potentially work with it. We probably won't have to change our code very much, but it will probably change the runtimes. It was for a new attack they called Spectre 1.2 and 1.3. Oh god, too many of these. Turns out that building CPUs is hard. and this, like, we're still so young in programming that like we're just building vulnerabilities and we have no clue that we are. I'm just also hoping that it wasn't an injected, like, purposeful backdoor that they put in that caused this. Because if that was, then that's affecting, like, that decision affected everybody. Creating a new thread with spawn. To create a new thread, we call the thread spawn function and pass it a closure. We talked about closures in chapter 13, containing the code we want to run in the new thread. The example in listing 16.1 prints some text from the main thread and other text from a new thread. Okay, so use standard thread, use standard time duration, function med thread spawn, and then we have a this closure that doesn't take in any parameters. For I and 1.10 print line high number from the spawn thread. So let's do this. So we'll come in here and do cargo new threads. All right, so what is it we need again? We need standard thread and standard time duration for this exercise. So there's thread, and then there's use standard time duration. You know, one thing that would be really awesome for VS Code is if not only just said like pub struct duration, it had like a very short, like the doc, maybe like the doc string or the documentation would. That would be pretty cool. So we use standard thread, we use standard time duration. Then inside of here, we want to call thread. So thread spawn, and then this takes in a function, or rather a I keep wanting to call it callback, but rather this closure, which is being past them to call when, like, during its time. So we then want just a standard for loop, it sounds like, for that I in 1.10. And what are we doing in here? We're just gonna print line, like print something, print the number in here, and we're gonna thread sleep the duration from millis, just so like sleep 1 millisecond between each one. They're gonna do the same thing over here, and see whether or not they run all of this at first, or if they're sort of interspersed. Okay, so we want to print something. So we're going to print line, hello, close this, from thread. And we are just going to print I out here. And then we're going to have that's pulling information from RLS, I believe, so we need the RLS devs to make it a feature. That would be pretty cool, though, to have a little bit more description in that. Duration. All right, how does duration work? Oh, thread sleep. Okay, so that's what we want to do. Thread sleep, and then we want its duration from millis. Duration from millis, and we'll just do 1 milli here. Now, what are you yelling about? Expected. Oh, so yeah, I don't want to return this thread, so semicolon. I don't need to use a let in here. All right, so that's the thread, and then we want to do another print line. So for I in 1.5, gonna print line I am not from a thread I. Since you're using RLS, you really should make sure nightly is updated every day, so you have the latest version of RLS. They've been changing that a lot recently. Well, I haven't been using nightly. Do I need to, like, if I like update nightly but then don't use it actively and I'm using just the normal stable, does that affect RLS? I would guess that it wouldn't, right? And then I want to, RLS is always run for nightly regardless. Oh, interesting. Okay, I could try that. And then this one, this is also really interesting because this is thread sleep duration from in this one, which is not inside of the spawn thread. So thread sleep duration from millis 1. All right, let's run this and see what happens. Cargo run. So we can see I am not from a thread ends up running first. So this ends up running like the first one right here. Hello from a thread runs second right here. Also notice we only go up to 5. So we spin off this thread and it starts running over here. And we have the main thread, which is of course like our main program here. And it's running, like we can almost imagine it's its own thread, but it's like it's running this process. And as soon as it finishes, it exits out, cleans up everything, and tells the operating system, I'm done, see you, bye. And this thread is just stuck hanging, but it gets cleaned up by the operating system because we no longer need it. But it also means it stops running. Note that with this function, the new thread will be stopped when a main thread ends, whether or not it has finished running. The output from this program might be a little different every time, but it will look similar to the following. So that's pretty much what we got. The calls to thread sleep force a thread to stop its execution for a short duration, allowing a different thread to run. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads, and probably how the CPU handles threads too. And it might, architecture might be different on every computer. In this run, the main thread printed first, even though the print statement from the spawn thread appears first in the code. And even though we told the spawn thread to print until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread, or don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between threads. So what's going on here is the concurrency model of, okay, two threads, hit, and go switch back and forth. And as soon as something is I'll take a little time to process, I'll switch over here to work. Now, if we don't have, let's say we don't have this sleep inside the main thread. If we don't have this, and we don't have this at all, we just say hey, I want to print here, and I want to print there. What would we expect to happen? In this case, I kind of expect this to completely run and this not to run at all, because this is busy. That's why I don't put sleep. That's why we put sleep on the main thread, so we don't accidentally block the thread. Right, exactly. I just want to show this off to make sure that I understand how it's going to work. Yeah, exactly. So it just goes 1 through 4 and then stops. The other thread never works, even though it registers the other thread and launches it. It's waiting for it didn't launch on another 4. Waiting for all threads to finish using join handles. The code in listing 16.1 not only stops the spawned thread prematurely most of the time due to the main thread ending, but also can't guarantee that the spawn thread will get to run at all. The reason is that there is no guarantee on the order in which threads run. We can fix the problem of the spawn thread not getting to run, or not getting to run completely, by saving the return value of thread spawn in a variable. The return type of thread spawn is join handle. A join handle is an owned value that, when we call the join method on it, will wait for its thread to finish. Listing 16.2 shows how to use the join handle of the thread we created in listing 16.1 and call join to make sure the spawn thread finishes before main exits. So bring in standard thread and duration, let handle equals thread spawn, and then we just do our normal thing here. We do the previous normal thing here as well, but before we exit the main thread, handle.join unwrap, because I guess it's an option that it gives us out. So let's try it. So first of all, we're gonna say what this is. So let my thread, I don't know what else to call it right this second. And then down here, we're gonna do my thread dot join. Is it join? It is, okay. And then dot unwrap. Now, of course, if it was if it's a nil or something, I guess it would be a sum or a none. If it's a none, this will cause it to runtime error and panic out. Oh, this also won't work. Actually, this probably would work. It'd probably run all of these first and then all of these, because I'm forcing it to run. Let's do that. Yep, so all of the main threads first, and then all of these threads right after. Let's add the sleep back in, and then they'll run sort of somewhat concurrently. And then this one will run out of numbers, and then continue with the rest of them. Perfect. Calling join on a handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that thread is prevented from performing work or exiting. Because we put the call to join after the main thread's for loop, running listing 16.2 should produce output similar to this. Yep, that's I mean, this one, the main thread ran twice, but it's very close to what we had. The two threads continue alternating, but the main thread waits because of the call to handle.join and does not end until the spawn thread is finished. But let's see what happens when we instead move handle.join before the for loop in main. So what's going to happen to this, if I move this up here, we're end up going to saying, well, okay, this has to finish before we continue on. So we're going to get the threads count first. I did not mean to accidentally delete all the code. And there we go. Hello from the thread completely first, even though they have the timer and the sleep in there. The main thread will wait for the spawn thread to finish and then run its for loop, so the output won't be interleaved anymore, as shown here. Small details, such as where join is called, can affect whether or not your threads run at the same time. Using move closures with threads. The move closure is often used alongside thread spawn because it allows you to use data from one thread in another thread. In chapter 13, we mentioned that we can use the move keyword before the parameter list of a closure to force the closure to take ownership of the values it used in the environment. This technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. Not necessarily Rust-related question, but what happens to a thread that is too late to complete? Is there some trace of it somewhere in memory? If so, wouldn't that bring security issues with it? That's kind of dependent upon the operating system and the software. Since this is using one-to-one, it's allowing the operating system to handle all the threads. So when the main process dies, the operating system should see that, even if it crashes and can't run any of the cleanup code that would normally be set up. The operating system should see that, clean up the main memory, wipe that, release it all, but also release any threads that were running. Since the thread is technically a whole new program, it's closed and cleaned up by OS. Now, while that is normally true, there are zombies that can be created in computer applications, and that's just the operating system not cleaning it up properly. So we could end up with programs that are running that aren't running, if that makes any sense, and they're just sitting there taking up resources but not doing anything. If the memory for that reason wasn't cleaned up, then yeah, it's a security vulnerability. But probably not, and it's not going to be an easy security vulnerability to take advantage of. But that doesn't mean that a good hacker wouldn't be able to do something with it. Notice in listing 16.1 that the closure we pass to thread spawn takes no arguments. We're not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread's closure must capture the values it needs. Listing 16.3 shows an attempt to create a vector in a main thread and use it in a spawn thread. However, this won't yet work, as you'll see in a moment. So here's our vector. We create a thread, and then we print the vector out right there. Okay, outside the case of zombies, just always think of a thread spawning a new program with its own PID. Yeah, and then like nominally it should clean up afterwards, like 99.9% of the time. The closure uses V, so it will capture V and make it part of the closure's environment. Right here. Because thread spawn runs this closure in a new thread, we should be able to access V inside that new thread. But when we compile this example, we get the following error. So it may outlive borrowed value V. To force the closure to take ownership of V and any other reference variables, use the move keyword. So I think like one of the big things is there is a possibility that will end and then V would die for some reason, even though we have handle join unwrap here. Rust infers how to capture V, and because println only needs a reference to V, the closure tries to borrow V. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know if the reference to V will always be valid. Listing 16.4 provides a scenario that's more likely to have a reference to V that won't be valid. Okay, so another non-valid. So same exact code here. We have drop V. Okay, right, because now we're going to drop V, and now we're telling it to run here. Badness. If we were allowed to run this code, there's a possibility the spawn thread would be immediately put into the background without running at all. Actually, I would say a high likelihood that it would happen that way. The spawn thread has a reference to V inside, but the main thread immediately drops V using a drop function we discussed in chapter 15. Then, when the spawn thread starts to execute, V is no longer valid, so reference to it is also invalid. Oh no! To fix the compiler error in listing 16.3, we can use the error messages advice. By adding the move keyword before the closure, we force the closure to take ownership of the values it's using rather than allowing Rust to infer that it should borrow the values. The modification to listing 16.3 shown in listing 16.5 will compile and run as we intend. So here we have our vector, and the move keyword comes before right here. So let's try this. Now if we have something in here like hello from the thread, we can put our vector in. So let v equals vec 1, 2, 3. Then we're gonna spawn this thread. Maybe what I could say is move. So I don't need anything else. It's just tell it to move. So whatever is in here, it's going to be moved in. We have and now in here outside of the for loop, we can now just have our own print line that says the vector is v. All right, let's try running this. And here is the vector is this. So everything is fine now. Hold on, I think your logic is incorrect here. Also, I think I want to move this down here for maximum funness. The vec is still in main, so technically your code is doing nothing. Really, I'm printing the v in the thread here. So if I don't have this move, I should have the error. Right, so may outlive borrowed value v. So it's telling us we have to put the move in right here, which then fixes it. Was there something else? Did I just have a brain fart? I think it's more because it looks like it should be visible here. But because my print line is inside of the thread, it's inside this closure that's being executed by the thread, or no, not by the thread, inside of the thread, it is it's essentially a different process. So we have to think about that, even though it looks like it's the same. It's like it's really easy to like accidentally think, oh, it's running over here, when it's like actually almost like a different computer completely. What would happen to the code in listing 16.4 where the main thread called drop if we used a move closure? Would move fix that case? Unfortunately, no. We would get a different error because what listing 16.4 is trying to do isn't allowed for a different reason. If we added move to the closure, we would move v into the closure's environment, and we can no longer call drop because it's been moved on it in the main thread. We would get this compiler instead. Value moved into closure here, value used here after move. Okay, I thought your print line was under the, yeah. So what I'm hoping, I'm trying to tab in. I'm using four spaces to make it a little bit easier to see where things are. So I think it's this for loop makes it a little bit interesting because it's a block inside of a block. You know what might be easier to deal with this? I wonder, can I use a generator function? I wonder if I can do this. So function generate, so like, oh, I probably couldn't do that because like it's v, oh no, the v is right here. So count slowly. If I have count slowly, doesn't take anything in, and I want this to be a generator function, so I'm really just going to return. I wonder if I can just do this. I'm going to return this closure here, and let's copy this straight into here. Oh, and we need to return. We need to turn a type of. Can I do type function? Expected. Oh yeah, no, I can't do type function. Oh, we covered this like a while back, and I forgot how to do it. There's different like types for functions, aren't there? So it's like closure, rust, return. Type. Oh, that's the first edition. That's also the first edition. What is, or it's like really hard to like search for. It's because I want like return closure from function rust. There you go. Returning a closure. I don't want to do that. Implement trait. Well, but that's executing it, isn't it? There isn't a single return type. Each closure is a unique, unnameable type. Although maybe the compiler will help out. Mismatch type here. Yes, I know it's a mismatch type. Let's run the compiler and find out what type it should be. Found closure. Found type closure sort main or s. Okay, so found closure. Can I actually just type closure? Like, I don't think that works either. Yeah, cannot find type closure. Rust type closure. First edition, second edition. Okay, so the closure section probably has what we want. Although this is getting a little bit too like out down a rabbit hole for what we want to do. I may want to do something else. Because like I can just store this in a variable inside the main function. I was thinking about maybe doing because like I know there's different types. So the FN traits. Is there a capital FN? Is that what it is? I'm just not gonna worry about it too much because like I don't think I can do something like this. Nope, the precise format of FN family traits, type parameters is subject to change. Use parenthetical notation. Oh, FN once. So FN args, FN mute args. Okay. So can I do FN once? I would help, but functional programming is not my thing. I really need to work on it. I know some people that are good at that, but they haven't used Rust in a while, so they might not be able to help me here. I would love to be able to implement this sometime, but I don't think I can. So instead, I'm going to cut this out, not go down this rabbit hole, but instead, so we're gonna have our vector here like this, and we're also gonna say, let slow count equals this. Now, our thread here is move so move and then slow count. Expected one of an operator found let. That's because I completely forgot to semicolon there. Slow count. Expected one of, oh, interesting. So it doesn't like this. Does that's fine, which means I probably need to do move here. Which means if I want to do my Althur, good morning. Don't you need to box the function? Oh, yeah, I probably do. But as I was saying, it's probably not for this time. And at 7:50, I'm just gonna get this working in a variable, and then call it a day for that, and then maybe like go and remind myself how to do it so that later on I can. But I think you're right. I think I do need to box. It was saying something about box the function, so I need to like remember how to do that. I probably have the examples in this repo, and I'm just gonna go to read them. Fun exercise for after the stream. Yes, it is. Okay, so here we're gonna print line. The vector is v. I don't think you can keep the function on the heap, so unless box has another meaning here. So yeah, you're talking about the box smart pointer. And then there's box function, and are they the same, or are they? I don't know. I'm gonna have to look into it a little bit. Let's run this. It should exactly be the same as the last time it ran previously. And everything exactly the same, and we have our vector is this. So this is an alternate way of thinking about it, which might help sort of like keep things separated in the mind. I remember complaining about the Rust docs giving me two definitions here for box. It's possible that has two meanings, or that there are actually two boxes. Like it might be that there's two, like a data structure box and some other box. But it is 7:53. Let's take a look at where we are with this. Oh, this is the wrong. Go. Oh, we're close to the end here. What would happen to the code in listing 16.4 where the main thread called drop was used to move oh wait, we went through that. Rust ownership rules have saved us again. We got an error from the code in listing 16.3 because Rust was being conservative and only borrowing V for the thread, which meant the main thread could theoretically invalidate the spawn thread's reference. By telling Rust to move ownership of V to the spawn thread, we're guaranteeing Rust that the main thread won't use V anymore. If we change listing 16.4 in the same way, we're then violating the ownership rules when we try to use V in the main thread. The move keyword overrides Rust's conservative default of borrowing. It doesn't let us violate the ownership rules. With a basic understanding of threads and the thread API, let's look at what we can do with threads. Box fn means something like a function pointer to a function. Could be wrong. I heard nowadays you can use implement fn, but I haven't touched Rust in a while. Yeah, I'm gonna have to like look into like how to modern do it. Rust has changed a lot if you haven't used Rust in a while. It's from the people that I've used it a long time ago, I think it's a little bit easier, but no guarantee. Let's go ahead and start saving these off. First of all, we'll send this code up. So playing with threads. Guess I didn't need to push that because I'm gonna have to do another push right after this. Let's come back down and open up code here too. Okay, so currently at here, and our URL for that is right here. I will update this, updated where we are at, and pushing. All right, so yep, we updated properly. I'm gonna push this in. I'm gonna share the URL with you so you can like come and see the code that we just created and put up there. I have links to this repo in both the stream description and also the VOD that I'm going to upload to YouTube. I have a link to that there as well. This is chapter 16 threads, and we have a few more sections for this to get through. But it's going to be fun to like work with threads and work concurrently with them and sort of like see Rust's idea of how that's going to work safely. What I'm gonna do is I have a meetup tonight that I'm running. I'm an organizer of the Node.js meetup, and we're gonna be talking about an alternate to REST, basically using RPC or like gRPC or something like that to send messages back and forth over HTTP2 instead of like traditional HTTP. It's gonna be it's going to be a little bit interesting. The speaker is flying into Denver today to give that talk. I will be streaming it here on my stream, and then also archiving that video to YouTube as well. That, of course, if you're interested in Node.js and potentially using that in a different way, I would highly recommend stopping by. Of course, if you're in Denver, you can come by and pick up some pizza, get some drinks, and hang out with us. But until then, I'm gonna go get ready for my day. I have to pack up everything that I need for streaming, and then head off to work. What time is that? That is going to be 6:30 is when the meetup technically starts, and the talk starts around 7 p.m. Mountain Time. So if I open this up, here is the URL describing where that is. gRPC pretty much has been ported over to every language, so it's a good watch for everyone. It's also going to be interesting to see. This argument is going to be, can we replace standard HTTP with it? VOD it is. No problem. I'll make sure the VOD is put up to YouTube, and then that will be it. And it'll be this, like, if you are gonna watch it live, it'll be this exact same channel. So it's the Brookzerker channel here. So I don't think I have anything else. So it's 7:59. Thank you everybody for stopping by and watching. If you're liking these and you haven't already, I would please ask you to follow me here so that you can get notifications. It's 8 a.m. I can tell by the drop frames. Oh, 124 drop frames. Yeah, that is Comcast telling me they don't want me to stream anymore. Luckily, it's only 124. It's only 0.1%. But yeah, that's them telling me to go on and get ready for the rest of the day. All right, with that, I do really stream at the perfect time. Yeah, not for many other people here because they're still sleeping, but I guess that's what the perfect time means for them. All right, with that, I'm gonna get ready for the rest of the day. I hope that you all have a great day, and maybe I'll see you tonight online at the Node.js meetup. So turn off the stream, and if I don't see you tonight, I'll see you tomorrow morning.